High above the German coastline in the summer of 1944, something fundamental was shifting in the deadly calculus of aerial warfare. Luftwaffe pilots who had spent years mastering the art of survival were about to discover that their most dependable escape route had been sealed shut. The date was August 14th, and at 23,000 feet over Rostock, a Messerschmitt pilot was experiencing what would soon become a recurring nightmare for the German fighter force. The familiar sensation of the control stick vibrating as speed built up in a dive was nothing new. Every German pilot knew this feeling intimately. They had learned to trust it, to use it, to survive by it. When the airspeed indicator climbed past 500 kilometers per hour, that was the threshold where physics became their ally. Allied fighters, particularly those twin-boomed American P-38 Lightnings, would reach a point where continuing the pursuit meant losing control of their aircraft. The compressibility effect that plagued the Lightning at high speeds was common knowledge among the Jagdwaffe, and they had transformed this weakness into doctrine. Roll inverted, pull through into a split S, and continue diving. The pursuing Lightning would have to break off or risk a violent, uncontrollable tumble that could tear the aircraft apart or send it plummeting earthward with the pilot helpless at the controls. But on this particular August day, something was terribly wrong. The Lightning was still there, still tracking, still firing. The German pilot pushed his Messerschmitt harder into the dive, willing the aircraft to accelerate beyond the point where pursuit should be impossible. The airspeed continued climbing, but so did the Lightning behind him. At speeds where the American fighter should have been thrashing uncontrollably, it remained steady, its 8 machine guns and single cannon still aligned on target. The mathematics that had governed aerial combat for 3 years were being rewritten in real time, and German pilots were paying the price for their outdated equations. What the Luftwaffe could not have known was that a simple modification had transformed their enemy. Small aluminum plates, electrically actuated, deploying from the underside of the P-38's wings. The dive recovery flaps, as they would come to be called, represented a solution so elegantly straightforward that it belied the complexity of the problem they solved. Yet in warfare, simplicity often proves more valuable than sophistication, and these unremarkable metal surfaces would have an impact far beyond their physical dimensions. The story of how the Lightning gained this capability begins years earlier, in the spring of 1941, when the aircraft's compressibility problem was discovered not through systematic testing, but by accident. Major Signe Gilkey of the Army Air Corps found himself in serious trouble during a routine test flight. He had taken his Lightning to 30,000 feet, a perfectly ordinary altitude for the aircraft, and had entered what should have been a standard dive. But as his indicated airspeed reached approximately 320 miles per hour, everything went catastrophically wrong. The tail assembly began shaking with such violence that Gilkey feared structural failure was imminent. Then the nose dropped precipitously, forcing the aircraft into an almost vertical descent that he was powerless to correct. The Lightning, it seemed, had a hidden flaw that could kill its pilots without warning. What Gilkey had encountered was a phenomenon that would plague high-performance aircraft as they approached the speed of sound. As the Lightning dove and accelerated, the airflow over its wing-leading edges reached transonic velocities, even though the aircraft itself was flying well below the speed of sound. At these speeds, shock waves formed on the wing surfaces, disrupting the smooth flow of air that generated lift and control. More critically, these shock waves shifted the center of pressure backward along the wing, creating an aerodynamic force that pushed the nose down with such strength that the pilot's control inputs became meaningless. The elevator, normally responsive to the pilot's touch, lost its authority. The aircraft wanted to pitch nose down, and nothing the pilot did could prevent it. Engineers at Lockheed, the Lightning's manufacturer, recognized they had a serious problem. To understand it properly, they needed data that could only be gathered through wind tunnel testing. They arranged for a scale model of the P-38 to be tested at the Ames laboratory, operated by the National Advisory Committee for Aeronautics. The wind tunnel tests confirmed what Gilkey's near-death experience had suggested. When airflow over the wing leading edges approached transonic speeds, shock waves formed and the center of pressure moved aft. This created the uncontrollable nose-down pitching moment that made high-speed dives so dangerous for the Lightning. By 1942, this weakness was no longer a secret known only to American engineers and test pilots. German intelligence, systematic and thorough, had pieced together the Lightning's vulnerability through combat reports and interrogations of captured American pilots. The Luftwaffe, always quick to exploit enemy weaknesses, developed a standard response. When pursued by P-38s, German pilots were instructed to execute the first half of a split S maneuver and continue into a steep dive. The Lightning pilots, knowing their aircraft's limitations, would be forced to watch their quarry escape. This tactic was not merely theoretical. Combat reports from North Africa documented its effectiveness repeatedly. German fighters successfully disengaged using dive tactics in the vast majority of engagements where they attempted the maneuver. The psychological toll of this tactical disadvantage extended far beyond the immediate tactical situation. Luftwaffe pilots, aware they had a reliable escape option, approached engagements with confidence. They could be aggressive, knowing that if the situation turned unfavorable, they could simply roll inverted and dive away. American P-38 pilots, conversely, began fighting with the knowledge that any German pilot who wanted to leave could do so at will. This affected morale significantly. Pilots began hesitating in attacks, uncertain whether pressing an advantage was worth the risk when their opponent could disappear into a dive at any moment. The impact spread across P-38 units in both the Mediterranean and European theatres, creating a perception that the Lightning was fundamentally inferior to German fighters in certain aspects of combat performance. German fighter pilots developed their dive escape technique into a refined art. A single-engine fighter encountering P-38s would often execute a half-split S as part of their attack on bomber formations, knowing they could roll over and dive for the deck to escape both the bomber's defensive fire and any pursuing fighters. The tactic worked whether they were attacking or retreating, making it versatile and reliable. P-38 pilots found themselves in the frustrating position of achieving good tactical position, getting their opponent in their sights, only to watch them execute the standard dive escape and accelerate away into airspace the Lightning could not safely enter. What German intelligence did not know, could not have known, was that Lockheed's engineers had been quietly developing a solution since early 1943. The work was not proceeding in isolation or without direction. Kelly Johnson, the brilliant designer responsible for the P-38's creation, had understood from the beginning that compressibility would be a concern. He had consulted with leading aerodynamicists and had raised the issue in design reports early in the aircraft's development. However, he had encountered an unexpected obstacle. The National Advisory Committee for Aeronautics, which operated the wind tunnels necessary for high-speed testing, had initially refused to conduct the tests Lockheed requested. The stated reason was concern about damaging their wind tunnel facilities. This refusal meant that critical data about the Lightning's high-speed behavior was unavailable during the aircraft's initial development, and the compressibility problem only became apparent once production aircraft reached operational squadrons. By February of 1943, Lockheed had developed a solution and proven it effective through test flights. The concept was remarkably straightforward, which is often the hallmark of excellent engineering. Rather than redesigning the wing or attempting to prevent shockwave formation, the engineers decided to counter the effects of the shifted center of pressure. Small flaps, positioned on the wing's underside outboard of the engine nacelles, could be deployed during high-speed flight. When extended, these dive flaps created aerodynamic forces that shifted the center of pressure forward, restoring the elevator's authority and allowing the pilot to control the aircraft even when shock waves formed on the wing surfaces. The dive recovery flaps were unlike conventional flaps used for landing and takeoff. Instead of deploying from the wing's trailing edge, they extended from approximately mid-chord along the wing's lower surface. When deployed, they formed a distinctive V-shape and generated forces specifically designed to counteract the compressibility-induced pitch down. The mechanism was electrically actuated, with motors that could extend the flaps to 35 degrees in approximately 1.5 seconds, providing nearly instantaneous pitch control recovery when the pilot activated them. Tony Levier, Lockheed's renowned test pilot, conducted the dangerous work of proving the dive flap's effectiveness. His test flying had been instrumental throughout the Lightning's development, and now he took the modified aircraft to high altitude and pushed it into the steep dives that had nearly killed pilots like Major Gilkey. With the dive flaps, Levier discovered he could maintain controlled flight at significantly higher speeds than were possible in unmodified Lightnings. He could enter dives that would have resulted in violent, uncontrollable tumbling, deploy the flaps, and retain full authority over the aircraft. The solution worked, and it worked well. With successful testing complete, Lockheed moved to get the modification into combat as quickly as possible. The company manufactured over 200 retrofit modification kits designed to be installed on P-38 J-10 and J-20 variants already serving in European theatre. These kits were loaded aboard a Douglas C-54 transport for shipment to England, where they would be used to upgrade aircraft already in combat service. But in March of 1944, tragedy struck. The C-54, flying over the Atlantic, was mistaken for a German Focke-Wulf Condor by a Royal Air Force pilot and shot down. The friendly fire incident destroyed months of production effort and delayed the deployment of dive recovery flaps to P-38s already fighting in Europe. The loss was particularly unfortunate because it occurred during Tony Levier's 4-month tour of P-38 bases, where he was demonstrating the new capability and boosting morale among pilots who had been fighting with compromised aircraft. Despite this setback, production continued at Lockheed's Burbank facility. Through the spring of 1944, P-38Js coming off the assembly line were towed out to the ramp and modified in the open air because the modifications had not yet been incorporated into the production line itself. Workers installed the dive recovery flaps on aircraft that were otherwise complete, working outdoors to maintain production schedules. The modification was finally integrated into the assembly line in June of 1944, with the last 210 P-38J models being produced with factory-installed dive recovery flaps as standard equipment. While production ramped up and replacement modification kits were manufactured to replace those lost in the C-54 shoot-down, Tony Levier continued his demonstration tour of P-38 bases throughout Europe. He flew a specially modified Lightning that he had named Snafu Sperwan, which had been upgraded to P-38 J-25 specifications at Lockheed's Modification Centre near Belfast. What Levier demonstrated to combat pilots accustomed to the Lightning's limitations was nothing short of revolutionary. At bases like King's Cross, he would take his modified Lightning to 25,000 feet while groups of pilots watched from the ground. Then he would roll the aircraft into a vertical dive, the kind of maneuver that 8th Air Force wisdom held to be suicidal in a P-38. Pilots on the ground would rush out, expecting to witness a crash. Instead, Levier would pull out smoothly, without apparent effort, then perform several low-level single-engine rolls for emphasis. The demonstrations were transformative for pilot morale. Men who had been flying with the knowledge that their aircraft had a critical flaw suddenly saw proof that the problem had been solved and that modified aircraft would soon reach their squadrons. By August of 1944, the first P-38 J-25s with factory-installed dive recovery flaps began arriving at combat units in meaningful numbers. The impact on combat dynamics was immediate and profound. German pilots who had relied on the dive escape for 3 years suddenly found themselves pursued through maneuvers that should have guaranteed their escape. P-38S that should have been tumbling out of control were instead maintaining steady pursuit, their guns continuing to track targets through dives that reached speeds previously impossible to sustain in controlled flight. The legendary fighter pilot Robin Olds, who would go on to even greater fame in later conflicts, experienced both sides of the compressibility problem during his time flying P-38s. In one early incident, flying an unmodified Lightning, Olds dove to assist a fellow pilot and in his excitement dove too fast. The aircraft entered compressibility, and Olds found himself subject to the violent, uncontrollable pitching that had claimed other pilots. Only by reaching the denser air at lower altitudes did he regain control and manage to pull out of the dive. The G-forces generated during his recovery were so extreme that his canopy window blew out. Later, flying P-38s equipped with dive recovery flaps, Olds noted the dramatic difference in handling characteristics. The flaps shifted the center of lift back forward when compressibility effects tried to shift it aft, preventing the aircraft from attempting what pilots described as an outside loop. The transformation in aircraft behavior was profound and immediately apparent to anyone who had experienced both versions of the Lightning. Operating the dive recovery flaps was straightforward. A simple electrical switch mounted on the control yoke activated the system. When the pilot threw the switch, electric motors extended the flaps to their full deployment in about 1.5 seconds. The flaps provided an instant nose-up pitching moment that countered the nose-down pitch induced by compressibility. Pilots were instructed to deploy the dive flaps before reaching critical Mach number when entering steep dives. This preventive deployment kept the aircraft from ever entering the violent, uncontrollable phase that had characterized compressibility encounters in unmodified Lightnings. The procedure was simple enough that it became second nature, and pilots who properly employed their dive flaps found they could pursue enemy fighters through any dive profile without fear of losing control. For the Luftwaffe, the discovery that P-38s could now follow them through steep dives represented a fundamental shift in tactical calculations. The dive escape had been their insurance policy, a technique that had saved countless German pilots when they found themselves at a disadvantage. Until the J-25 variant arrived, P-38s were easily avoided using this tactic. German fighters could disengage from combat at will, making the Lightning less threatening than its performance specifications suggested it should be. A Luftwaffe pilot not wishing to continue a fight could simply perform the first half of a split S and continue into a steep dive, confident that any Lightning pilot would be reluctant to follow. The loss of this escape option forced fundamental changes in German tactics. Pilots who had trained for years with the dive escape as their fallback position suddenly found themselves vulnerable in situations they had previously considered manageable. They had to remain in turning fights where the P-38's concentrated forward firepower proved devastating. 4 50 caliber machine guns and one 20mm cannon, all mounted in the nose and all firing along the same axis, made the Lightning a lethal gun platform. German pilots had always known this, but they had been able to avoid extended engagements by diving away. Now they had to face that firepower in prolonged combat. German technical intelligence eventually examined crashed P-38 wrecks and discovered the dive recovery flaps. Luftwaffe engineers could see the modification and understand its function. However, by late 1944, Germany's deteriorating industrial situation made any meaningful response impossible. Production lines were disrupted by constant Allied bombardment. Resources were critically short. The focus had shifted to revolutionary technologies like jet fighters rather than incremental improvements to existing designs. Even if German engineers had developed a similar system for Focke-Wulf or Messerschmitt fighters, implementing it across the thousands of aircraft in service would have been beyond Germany's capabilities at that stage of the war. The statistical evidence of the dive recovery flaps' impact was clear in fighter group reports. Before August of 1944, German fighters successfully escaped P-38 pursuit through dive tactics in the majority of encounters where the maneuver was attempted. After P-38 J-25s reached combat units in meaningful numbers, the successful escape rate dropped dramatically. P-38 victory rates increased correspondingly. The modification had transformed the Lightning from an aircraft with a significant tactical weakness into a fighter that could pursue German aircraft through any escape maneuver. The hunters had indeed become the hunted, and the psychological impact on German pilots was as significant as the tactical advantage gained by the Americans. The development and deployment of dive recovery flaps had been a race against time that many outside Lockheed didn't fully appreciate. Late in 1943, several hundred field modification kits were assembled with the intention of giving P-38s in North Africa, Europe, and the Pacific a fighting chance against compressibility. The modification process demonstrated American industrial flexibility and the ability to adapt production to meet combat requirements. At Lockheed's Burbank facility, skilled workers could install dive flaps on existing aircraft in a matter of hours. Field modification units in England, using kits that eventually arrived safely after the loss of the first C-54 shipment, could complete installations in combat theatres without requiring aircraft to return to the United States. The program's success proved that sometimes the best solutions are the simplest ones. Each dive recovery flap measured approximately 18 inches by 35 inches, positioned just outboard of each engine nacelle on the wing's lower surface. When deployed, they created just enough aerodynamic disruption to prevent the dangerous aft shift of center of pressure without significantly reducing the aircraft's speed or maneuverability. Kelly Johnson's understanding of the problem from the design phase, combined with systematic testing and the courage of test pilots like Tony Levere and Milo Burcham, who alternated flying dive tests to observe the aircraft's performance at transonic speeds, had produced a modification that solved one of the Lightning's most serious deficiencies. Despite testing having proven the dive flaps effective in improving tactical maneuvers, the 14-month delay between successful tests and production implementation limited how many aircraft received the modification during the war. Only the final half of all Lightnings built had dive flaps installed as an assembly line sequence. Earlier aircraft had to wait for field modification kits, and many P-38s serving in combat never received the upgrade. Nevertheless, the impact on those aircraft that did receive the modification was transformative. The dive recovery flap program's contribution to understanding transonic aerodynamics extended far beyond its immediate tactical impact. 17 months passed from the initial discovery of the compressibility problem before engineers fully understood what caused the Lightning's nose to drop. The data gathered from wind tunnel tests, flight tests, and combat reports helped establish fundamental principles that would guide the development of supersonic aircraft in the post-war years. The lessons learned about high-speed flight control, about managing aerodynamic forces that changed dramatically as aircraft approached the speed of sound, and about maintaining pilot control in regimes where conventional aerodynamic relationships broke down, all contributed to the body of knowledge that would make supersonic flight practical. In the Pacific theatre, the P-38 had always performed better than in Europe. Combat rarely occurred above 20,000 feet, and the engine and cockpit comfort problems that plagued European operations never became significant issues for pilots operating in the Pacific. While compressibility was less of a concern due to lower combat altitudes, dive recovery flaps still provided tactical advantages. P-38 pilots in the Pacific could pursue Japanese fighters through any maneuver, maintaining the Lightning's dominance in a theatre where it achieved its greatest success. Major Richard Bong, who became America's ace of aces with 40 confirmed victories, flew P-38s exclusively in the Pacific. While most of his victories came before he received flap-equipped aircraft, the modification enhanced an already superior platform and contributed to the Lightning's continued success against Japanese opponents. The story of dive recovery flaps illustrated how wartime pressure could accelerate innovation dramatically. Under normal circumstances, the process of identifying a problem, developing a solution, testing it thoroughly, and implementing it in production might have taken many years. Under the pressure of combat operations, with pilots dying because of the problem and tactical advantages being lost, the timeline compressed to approximately 16 months from problem identification to combat deployment. This was a timeline that would have been impossible for Germany's stressed industrial base in 1944, demonstrating another dimension of Allied advantage beyond simple numbers. For German pilots, the loss of their dive escape capability meant more than just tactical adaptation. It represented a psychological blow that contributed to declining Luftwaffe effectiveness in the war's final months. Pilots who had relied on the dive escape as their ultimate safety valve suddenly found themselves without that option. The confidence that comes from knowing you have a reliable escape route disappeared. In its place came uncertainty and the knowledge that every engagement might become a fight to the death because disengagement was no longer guaranteed. This loss of confidence, combined with fuel shortages, pilot training deficiencies, overwhelming numerical inferiority, and the appearance of Allied jet fighters, contributed to the Luftwaffe's collapse in the final months of the war. The extensive documentation of the dive recovery flap program proved invaluable for post-war aerospace development. Every test flight was recorded in detail. Combat reports were analyzed systematically. Modification procedures were documented thoroughly. This body of knowledge established principles of high-speed flight control that influenced aircraft design for decades. The nose drop and loss of control were never fully remedied in the sense that the fundamental physics of transonic flow couldn't be eliminated. But the dive recovery flaps provided a practical solution that allowed pilots to maintain control when diving at high speed. This principle of using control surfaces to counter adverse aerodynamic effects would be applied to numerous post-war aircraft designs. During Operation Market Garden in September of 1944, P-38s demonstrated their new capability in large-scale fighter engagements over Holland. The Luftwaffe recognized the importance of stopping the Allied airborne operation and committed some of its best remaining units. In the resulting air battles, P-38 pilots found they could pursue German fighters through any evasive maneuver. The favorable kill ratios they achieved would have been impossible months earlier, when German pilots could simply dive away from any engagement that turned unfavorable. The modification had arrived at a critical juncture in the war when every tactical advantage contributed to the final push toward victory. Through the winter of 1944 into 1945, dive recovery flaps continued proving their worth in combat. During the Luftwaffe's Operation Bodenplatte on January 1, 1945, their last major offensive action, German fighters attacked Allied airfields in an attempt to destroy aircraft on the ground and regain some measure of air superiority. P-38s intercepted many of these raiders as they attempted to escape after their attacks. German pilots had planned their escape routes based on their ability to dive away from pursuit, a tactic that had worked reliably for years. Instead, they found P-38s maintaining contact through dives that should have guaranteed escape. This unexpected pursuit capability contributed significantly to the operation's heavy losses, from which the Luftwaffe never recovered. The surprise of being followed through what should have been sanctuary added to the chaos and confusion of an operation that was already poorly coordinated and executed. The influence of dive recovery flap research on early jet fighter development was both direct and significant. When Chuck Yeager broke the sound barrier in the Bell X-1 in 1947, that aircraft incorporated design elements derived directly from P-38 compressibility research. The adjustable horizontal stabilizer that helped Yeager maintain control through transonic flight evolved from principles discovered during dive recovery flap development. Engineers understood that control authority needed to be maintained even as aerodynamic forces changed dramatically, and they designed systems to ensure pilots could keep their aircraft under control throughout the entire speed range. From a purely financial perspective, the dive recovery flap program represented an excellent return on investment. The entire program cost approximately $2.8 million in 1944 currency. Based on previous loss rates, this investment saved an estimated 260 P-38s from compressibility-related losses between August 1944 and May 1945. Each P-38 saved represented $97,000 in replacement costs, not accounting for the invaluable experience of trained pilots who would have been lost with those aircraft. The improved combat effectiveness, measured in additional enemy aircraft, destroyed because P-38s could now pursue targets through any maneuver, provided returns that far exceeded the program's cost. In purely economic terms, it was a remarkably efficient use of resources. The introduction of dive recovery flaps required significant changes to P-38 pilot training curricula. The Army Air Forces updated training syllabi to include proper flap usage, with pilots practicing high-speed dives and controlled recovery before being sent to combat units. Standard operating procedure called for deploying flaps at 450 miles per hour indicated airspeed, or at the first sign of buffeting, whichever came first. Pilots learned to hold deployment for at least 3 seconds before attempting recovery, avoiding structural damage from sudden deceleration forces. The training proved highly effective. Pilots who received proper dive flap instruction experienced dramatically fewer compressibility-related accidents compared to those who had flown earlier P-38 models without the modification or proper training in its use. Despite their deteriorating situation, German engineers attempted to develop their own solutions. Focke-Wulf engineers proposed installing spoilers on FW-190D model wings to achieve similar effects to the American dive recovery flaps. Testing showed the concept had promise, but modifications never reached production units before the war ended. Messerschmitt considered variable incidence tailplanes for the Bf-109K that could be adjusted in flight to counteract compressibility effects. Prototypes were actually built and tested in early 1945, demonstrating that German engineers understood the problem and were working towards solutions. However, the war ended before implementation could proceed beyond the prototype stage. The Messerschmitt Me 262 jet fighter, which began operations in summer 1944, avoided compressibility problems altogether through its swept-wing design, but with fewer than 1,400 Me 262s produced compared to tens of thousands of conventional fighters, this hardly solved the tactical problem facing the bulk of the Luftwaffe. The successful concealment of dive recovery flaps until combat deployment represented a significant intelligence victory for the Allies. Despite German agents having access to information from neutral countries, and despite the general difficulty of maintaining secrecy about American aviation developments, the Germans had no advance warning of the modification. Security measures included additional secrecy agreements for Lockheed workers, separate storage of technical drawings, and restricted information even among P-38 pilots until they actually received modified aircraft. This operational security multiplied the tactical advantage through surprise. The first time German pilots discovered that P-38s could follow them through steep dives was when it happened in combat, eliminating any opportunity for the Luftwaffe to develop countermeasures or adapt their tactics in advance. The contribution of dive recovery flaps to maintaining Allied air superiority in the war's final months supported ground operations that led directly to victory in Europe. Air superiority allowed close air support missions to proceed with minimal interference, interdicted German supply lines effectively, and protected Allied ground forces from Luftwaffe attack. Every tactical advantage contributed to this overall superiority, and the dive recovery flaps represented one more capability that German pilots had to account for and that limited their options in combat. The significance of dive recovery flaps gained widespread recognition in post-war analysis. The United States Strategic Bombing Survey, which conducted comprehensive analysis of the air war, identified the loss of dive escape capability among the top tactical factors contributing to Luftwaffe defeat. This wasn't hyperbole or exaggeration. German veterans interviewed decades after the war consistently cited the P-38's new diving capability as a shock that fundamentally changed air combat in ways that put them at severe disadvantage. They had trained for years using dive escapes as a fundamental tactic. Losing this option forced improvisation with inferior alternatives at a time when they were already facing overwhelming odds in nearly every aspect of aerial combat. Today, surviving P-38s with original dive recovery flaps serve as physical testaments to wartime innovation. Museums display these aircraft with the flaps clearly visible, helping visitors understand how relatively small modifications could have strategic impact. The Smithsonian National Air and Space Museum maintains complete technical documentation for the program, including original wind tunnel test data, design notes from Kelly Johnson and his team, combat reports analyzing the flap's tactical impact, production blueprints showing exact specifications, and field modification instructions that were used to retrofit earlier aircraft. This archive remains invaluable for aerospace historians studying the development of high-speed flight and for engineers examining historical approaches to solving aerodynamic problems. The dive recovery flap story is taught at aerospace engineering schools and military academies as a case study in rapid problem-solving under extreme pressure. Students learn not just the technical aspects of the solution, but also organizational and leadership lessons about innovation during crisis. Key takeaways include the importance of clear problem definition before attempting solutions, the value of simple solutions over unnecessarily complex ones, how implementation speed can multiply tactical advantage even when the solution itself is modest, and how small modifications can have impacts far beyond what their physical scale might suggest. These lessons remain relevant to modern military and aerospace development programs. Behind every technical achievement are individuals whose dedication, skill, and courage make success possible. Kelly Johnson worked tirelessly to understand compressibility and develop practical solutions. Tony Levier risked his life proving those solutions worked, pushing aircraft to their limits and beyond to gather the data engineers needed. Engineers like Ward Beeman and Carl Haddon created reliable systems under intense time pressure, working with the knowledge that pilots' lives depended on their work. Assembly line workers at Lockheed modified aircraft outdoors in all weather to maintain production schedules when the modification hadn't yet been integrated into the production line. Field maintenance crews installed modification kits under combat conditions, often working near the front lines to get the upgrade to pilots as quickly as possible. Each person contributed to a program that saved lives and shortened the war, even if most remained anonymous and unrecognized outside their immediate circles. Modern fighter aircraft incorporate lessons learned from P-38 dive recovery flap experience in ways that would have seemed like science fiction to World War II pilots. Fly-by-wire systems automatically deploy control surfaces to maintain flight control at extreme speeds without requiring pilot input. Computer-controlled systems accomplish what mechanical flaps achieved in 1944, just with far greater precision and speed. Yet the principle remains fundamentally unchanged, maintaining control when aerodynamics threaten to take it away. Technology has advanced from aluminum plates and electric motors to digital flight control systems and computerized stability augmentation. But the underlying concept that Kelly Johnson and his team pioneered continues to influence every modern fighter aircraft. The timing of dive recovery flap deployment proved critical to the war's outcome in ways that might not be immediately apparent. Had the modification been delayed another 6 months, German jets might have entered service in sufficient numbers to offset some of the advantage. The Me-262, despite its many operational problems, was substantially faster than any Allied fighter and could have changed the tactical equation if deployed in large numbers. Instead, the dive recovery flaps helped maintain Allied air superiority through the war's decisive final campaigns, ensuring that close air support, interdiction, and strategic bombing could continue without significant interference. The modification arrived at precisely the time when it was most needed, when Allied forces were driving into Germany and needed complete air superiority to support their advance. The dive recovery flap program exemplified successful wartime innovation in ways that military historians and industrial analysts continue to study. It demonstrated that effective solutions often came not from revolutionary breakthroughs requiring years of research, but from incremental improvements addressing specific problems identified through operational experience. The program showed how industrial flexibility, rapid prototyping capabilities, and production adaptation could provide tactical advantages faster than enemies could respond, even when those enemies knew about the problem and were trying to develop their own solutions. This model of innovation, taking a problem identified in combat, developing a practical solution quickly, testing it thoroughly but efficiently, and deploying it to operational units as fast as possible, would influence American military development throughout the Cold War and beyond. The story of P-38 dive recovery flaps ultimately proves that in warfare, small innovations can have impacts far exceeding what their modest nature might suggest. Simple aluminum plates and electric motors solved a problem that had seemed insurmountable to many. They transformed the P-38 from a compromised fighter with a critical weakness into a dominant aircraft that could pursue enemies through any maneuver. German pilots who had escaped through steep dives for 3 years suddenly found their sanctuary had become a trap. P-38s followed them into dives that should have guaranteed escape, maintaining steady control while German pilots watched their reliable escape route close off before their eyes. The psychological shock of losing their last reliable escape option combined with the tactical disadvantage to accelerate Luftwaffe decline precisely when Germany could least afford any additional setbacks. The P-38's overall service record shows mixed results that historians continue to debate. Much of the variation in performance appears to reflect more on how the aircraft was employed rather than on fundamental flaws with the design itself. The P-38's engine troubles at high altitudes primarily affected the 8th Air Force operating from England. One significant reason was the inadequate cooling systems of the G and H models, which proved unsuitable for the sustained high-altitude operations required in the European theatre. The improved P-38J and L models had tremendous success flying from Italy into Germany at all altitudes, suggesting that when properly developed and employed, the Lightning was a formidable fighter. The dive recovery flaps solved the one remaining major flaw in what was otherwise an excellent aircraft. The flaps proved that American industrial capability extended well beyond simple mass production into rapid innovation and implementation. While Germany pursued wonder weapons that never materialized in meaningful numbers, America perfected practical improvements that won battles day after day. From conception in Lockheed's engineering offices to deployment over European skies, the dive recovery flap program demonstrated American strengths in problem-solving, industrial flexibility, and implementation speed. The modification that German pilots never expected transformed aerial combat in the war's crucial final year, shifting the balance at exactly the moment when Allied forces needed every advantage they could gain. The legacy of dive recovery flaps endures in every modern fighter aircraft that maintains control at extreme speeds, in every aerospace engineer who learns to seek simple solutions to complex problems, and in the historical lesson that in warfare, innovation and implementation speed can be as decisive as raw numbers and firepower. The Germans never expected that such a seemingly simple modification could neutralize their most reliable survival tactic. They never anticipated that American industry could develop, test, and deploy a solution faster than German intelligence could even detect its existence. Most critically, they never imagined that the P-38s they had easily escaped from would suddenly be able to follow them through any dive, no matter how steep or how fast. Those small aluminum plates represented the difference between escape and capture, between survival and death, between tactical advantage and disadvantage. The dive recovery flaps proved conclusively that sometimes the most powerful weapons are not the most complex or sophisticated, but rather the most elegantly simple solutions applied to critical problems at exactly the right moment. The Germans discovered too late that American ingenuity had transformed what they considered their sanctuary into a deadly trap. The dive that had meant certain escape for 3 years now led only to destruction, with P-38 Lightnings following them down with steady control and deadly accuracy. The hunters had indeed become the hunted, and the skies over Europe in the final year of the war would never be the same. Every German pilot who rolled inverted and pushed into what had been a reliable escape dive now had to wonder whether today would be the day they encountered a P-38 with dive recovery flaps, whether this dive would lead to safety, or whether they were simply accelerating toward their own destruction with an American fighter following every meter of the way down.